This is a review of the problem from tutorial 09, questions 2A and B, with a little bit of an introduction, talking about caching strategies and focusing on direct map caching in particular. So here's the basic problem. Recall the mapping from a memory address to cache block from our slide 52 in module 3. The formula being the cache index is equal to the address divided by the block size, where that's an integer division, mod m. And we're going to assume that we have 8 blocks of cache memory, that the block size is 4 words, and that there are 128 memory addresses altogether in main memory. So we want to consider the following accesses to memory, and we'll go through those individual accesses later on. We're going to start by considering a model of main memory. So we have 128 addresses, and there are 4 words per block. That means that there is a total of 32 blocks. So here we think of our memory addresses, and each of these addresses are labeled with, in this case, a decimal number version of that address. But we now are going to be thinking about main memory in terms of blocks rather than just individual addresses. And this comes back to the idea of spatial locality, where if we're going to access a particular memory address, there's a good chance that we want to access other memory addresses that are close to it in the near future. So we identify a block of memory in main memory, and in this case we're saying our block size is 4. So here we have 4 memory addresses clustered together, and they have a single identity with what I'm going to refer to as a block ID. I have both the decimal number version and the binary number version of this block ID identified here. I'm going to be working with binary numbers in terms of addresses and caching in the later explanations. So in this case, we have 32 blocks in total. So the first 4 addresses are clustered together under block 0. The next 4 would be under block 1. The next 4 under block 2, and so on, up to the last 4, which would be identified as block 31. What we want to notice here is that there's something in common with all the addresses within a single block. So let's consider the addresses in block 5. So the addresses in decimal are addresses 20, 21, 22, 23. In binary, we see that those addresses are in sequence. They end with 00, 01, 10, and 11. In each block, the memory addresses, the sequential memory addresses within that block will be 00, ending with 00, 01, 10, and 11. But what we notice is that the first 5 bits in this case are all the same. We have, our addresses are 7 bits in total because we have 128 different memory addresses, and 2 to the power of 7 is 128. So we need 7 bits to identify each of those addresses. But within a block, all of the first 5 bits of all of those addresses are going to be exactly the same. And so this now becomes the way that we can identify a block ID within our main memory. So notice that the block ID for block 5 here is the first 5 bits of all of the memory addresses within that block. The block ID for block 2 would be the first 5 bits of all of the memory addresses of 8, 9, 10, and 11 if we were to convert those into binary. And the block ID for 31, block 31 for example, all of the memory addresses 124, 125, 126, 127, they would all start with 5 ones in their bit sequence version of that address. So we can start by taking our address, converting it into a binary number. Then we take that binary number and look at we eliminate the last 2 bits in this case because the block size is 4, and 2 to the power of 4 is, the block size is 4, and 2 to the power of 2 is equal to 4. So we ignore the last 2 bits. Those will all be different within a block. And then whatever is remaining, in this case, there are 5 bits remaining because the the address was 7 bits to begin with and we're ignoring the last 2 bits, we have 5 bits to identify the block address. So that gives us a basic overview of the memory situation. Now let's take a look specifically at what happens if we want to deal with a DirectMap cache. So I'm going to start by taking my addresses here, 2, 3, 16, and so on up to 11. And I'm going to create a little table. I have the 7-bit address for each of these in binary. And then I'm going to, again, because of our block size and because of our the number of addresses in main memory in total, we know that the block IDs are all going to be 5-bit numbers, which are going to be basically the first 5 bits of an individual address. So we see the block ID for address 2 is 00000, and then we can fill in the rest of the table. Now we want to think about how do we actually manage the cache. So let's start by taking a look at what happens when we access address 2. Well, the first thing that we notice is that the valid tag is no, starts as no for all of the cache to begin with, because there's nothing in the cache to start. So the cache is absolutely empty. We have a cache index column here. This is an 8-block cache, so there are 8 different index values, and so we need 3 bits to identify each index value, starting at 000 and then 001 up to 111. And so from the block ID, we're going to take the last 3 bits to figure out what is the index position in the cache that this particular block will map to. Now there will be, in our example here, there will be many, since there are 32 blocks altogether, and there's only 8 blocks in our cache, then there's going to be 4 blocks from main memory that are all going to be competing for the same position in the cache. So there will be 4 block IDs that all end with 000. And here we've encountered the first one. However, when we look at this index position, the first thing we're going to check is to see what's the value of the valid tag. And in this case, it's indicated as no, meaning there's nothing in the cache right now. So no matter what, if the valid tag is no, that means we have a miss. There's sort of no way around that. There wasn't anything in the cache. There's nothing to find there. So the next thing we have to do is now we add this particular block to the cache. And we need to switch the valid tag to yes. And we need to actually fill in the cache with the information, with that block of information from main memory. But we also have to let the cache know what particular block is in main memory. So again, we had 5 bits for our block address. We use 3 of those bits because 2 to the power of 3 is equal to 8, and that is our cache size, to identify the index position within the cache. And then the remaining bits, in this case 2 bits, identifies which of the 4 blocks from main memory is actually in the cache at any given time. So in this case we use 00 to indicate that it is this particular block that's in the cache. And all of that information gets moved into the cache. And so the next time we encounter this particular block, we can check for the tag and see if we're in good shape here. So now let's take a look at what happens when we try and access address 3. Well, its block ID is 00000, and we immediately check our cache index and see that it's there's something valid in the cache at that particular place. And we notice that the tag value matches the tag value of our address 3 block. And so this counts as a hit, and there's no extra cost to this particular memory access. We find it in the cache, so we're happy about that. Let's move on to address 16. Now we're back to where we started with address 2. This is something that is, there's nothing in that particular index position within the cache, so we add it to the cache and we update the tag with the leftover bits from our block 16 address. So again, notice that the last 3 bits of block 16 match this index position, and the remaining 2 bits are what we fill in as our tag in our cache. We also update the valid tag to be yes, and we fill in the memory values. So this is indicating that block 00100 is now in the cache. Now we go to address 21. This is a new index position that doesn't have anything in it at 101. So we update that particular location. We update the valid tag to be yes, and our tag value is the leftover bits 00, and the block itself is 00101, which now appears in our data section of the table. Now we're going to address 13. We see a similar process of updating the cache at this point. Now let's take a look at address 64. So address 64, the block ID for it is 10000. And if we look at the index for the cache, we see that's 000. So 000 has a valid tag of yes. So there's something in the cache at index position 000. However, the tag value does not match the tag of our particular block ID. And so that means we're still looking at a miss here. There is something else in there. So at this point, what we need to do is we need to evict the memory of block 00000, and we're going to replace it with the memory block 10000, and we get this update. Next, we look at address 66. Well, here we see, again, the index position has something valid in it, and the tag matches, so that's a hit. So no further cost. Now we look at address 46. So address 46, the index position 011 has something there, but the tag doesn't match, and so that's a miss, and we're going to update that spot by evicting what was in there before and replacing it with the new block 01011. Next, address 19. Address 19 had an index of 100, and there was something there, and the tag matches our block tag of 00, so that's a hit. Now we have another miss where there wasn't anything in that cache index position, so our valid tag was no. So now we update that by filling in the data in block address 00010. Now we go back to address 3, and notice that this is an address that we directly accessed in the past. But unfortunately, what was there has been evicted in the meantime. And so we actually have another miss. We have here index position 000, and it is valid, but the tag doesn't match, and that's unfortunate that we ended up evicting something, especially considering the fact that we have 3 spaces in the cache here that we haven't even touched yet. So that seems like a waste of the cache, but that's just one of the consequences of DirectMap caching. We don't end up using all of the possible available cache space, so we have to accept that. So now we're going to evict what was there before, and we're going to update it with the block address 00000. Now we have a hit at address 22 because the index matches. There's something there, and the block tag is a match as well. We have a miss at address 4 because there's nothing in the cache at that point. The valid tag is no, so we're going to switch that valid tag to yes. And just note that once a valid tag moves from no to yes, it's never going to go back to no. There's no point in clearing a cache. That's a waste of energy. There's no value in that. So once the valid tag switches from no to yes, that's it. It stays yes forever. And then we go to address 14. This is a miss. There's no there's not a match of the tag of this particular block ID at the index position 011. So we update that with its new tag. Then we have a hit at address 6 because the tag at index position 001 matches our tag of 00 in this particular block ID. We have a miss in accessing address 43 because the tag does not match. Our tag in the cache is 00 and the tag in the block ID is 01, so that's a miss, and that's unfortunate because we end up evicting the value that was in there, which was actually where block 11 or address 11's block existed, and we immediately try and access address 11 again. And that's an unfortunate thing, again, because we have some space in the cache that we have never ever touched. But this is just part of the deal with dealing with direct map caching. So that gets us to the end, and here's our final cache state. And we have taken advantage of direct map caching and taken advantage of understanding how the bit sequences work for the addresses that will lead us to the block IDs, and then splitting up the block IDs into the cache index value and the tags within the cache. The second part of this will deal with associative caches.